Okay, now let us consider another example where the constraint is not in the simplest form. Okay, before that, let's read through the question here. So a rectangle is to be inscribed in the ellipse 4x squared plus 9y squared equals to 36. So use the eigenvalue methods to find the non-negative values of x and y that produce the inscribed rectangle with maximum area. So remember, optimization involves two components. The components that you want to optimize and the constraint. Apparently, in this case, the constraint will be the ellipse. And the components that you want to optimize is the area. The area of the rectangle. So if I'm going to express in the form of diagram, it will look like this. So you have an ellipse and inside you have a rectangle. So your rectangle can be in this form, can be in this form, can be in any of the shape. Okay, that's why we want to find out what shape will give you the maximum area. And then we know that for a rectangle, since it is in the symmetrical diagram of ellipse, so the rectangle can be obtained if you know the x component here and the y value here. So define an equations for the area of rectangle equal to 4xy, and the problem is to maximize the quadratic form z equals to 4xy. So maximize means that it is a kind of optimization because you want to find out the maximum value. So this will be the component for you to optimize, subject to the constraint of the ellipse 4x squared plus 9y squared equals to 36. Now since the constraint is not in the simplest form, x squared plus y squared equals to 1, so the first step you need to do is define a new variables for the constraint such that you can get the simplest form. Okay, now I'm going to rearrange. So you divide both sides with 36 such that you end up with 1 here, and then this is actually x squared divided by 9 plus y squared divided by 4 equals to 1. So 9 is 3 raised to the power of 2, right? So 4 is 2 raised to the power of 2, and then you have a x over 3 y over 2 here. So let's define x1. So this will be the new variable equivalent to x over 3, y1 equivalent to y over 2. So when you substitute these new variables into the equation, you get x1 squared y1 squared equals to 1. And now it looks like the simplest form, right? It is similar as the simplest circle form. But then, since we introduce a new variable for the constraint, we have to introduce it to the component that you want to optimize as well. So the 4xy, you have to convert it into the new variables x1 and y1. So from the definition here, you can rearrange it to get the value of x and y, so that you end up with the z equivalent to 24 x1 y1. This is because you can't deal with a case where you have two sets of variables. Okay, if you are dealing with x1 y1, then the other components must be x1 y1 as well. So now you have reduced everything. You have defined a new variable such that the constraint has been expressed in the form of the simplest form of circle equations. Though the second step will be the same as the previous example, so express the quadratic form in the matrix notation. So you have a 24 x1 y1, you have to express it in the form of x transpose ax. So in this case here, if you don't know how to get it, the matrix A here, so this should be x squared y squared xy and xy. We don't have the value for x1 x squared and y squared, that's why we have a 0 0, and xy will be shared between these 2 and 3. 24 must be divided by 2, so you have a 12 12. Now the step 3 will be to find the eigenvalues, and there's a tips for your eigenvalues and eigenvectors. So depends on the questions. Okay, your question might be asking you to find the maximum and minimum, or maybe just the maximum, or maybe the minimum. So if the question is asking you to find the maximum or maybe the minimum, you just need to deal with one of the eigenvalues. Remember, the lambda is the maximum or the minimum of the corresponding z value at the end of the solutions. So if you just need to find the maximum, just take the largest eigenvalues. If for minimum, take the smallest one. If maximum and minimum, then you are so unlucky, you have to do both. And in this case, we want to find the maximum area, so we get the largest eigenvalues. And another thing is that logical thinking, because area cannot be negative value. So if you have a lambda equals to negative 12, right, so this is automatically out because you can't have a negative area. So once you have the eigenvalue, find the eigenvectors. So you only consider one of the eigenvalues here. So you have your u1, which is 1 and 1. Normalize it, and then you end up with this. So the last step is to summarize it. So remember, when you summarize it, you have to answer it in the original variables x and y, because the eigenvectors that you found in step number 5 here is actually x1 and y1. So when you express it, the coordinate xy, you have to convert it into the, you have to convert the eigenvectors here x1 y1 into the x and y. So from our assumption here, x equals to 3x1, which we have obtained in the very early stage. So then you just need to substitute the x1 value into this equation, and you have this and this. So this will be your xy, and the eigenvalues will remain the same. So this is how you solve the optimization problem if your constraint is not in the simplest form. It's basically the same as the previous example, just that we have an additional step here where you need to define a new variable for it.